Welcome to this lecture. In the previous lecture, we have discussed about the wet etching process and the process how we can stop the etching. In this lecture, we will study about dry etching process. Dry etching removes the material by chemical reaction using the chemical reactive gases of plasma by purely physical methods that are sputtering and ion beam induced etching, or with the combination of both chemical reaction and physical bombardment, that is reactive ion etching. Conventional dry etching by the ions is slow in rate at about 0.1 micrometer per minute, but the plasma etching may increase the etching rate to 2 micrometer per minute. What is plasma? Plasma is partially ionized gas composed of equal number of positive and negative charges as well as some neutral molecules. How plasma can generate? Plasma can be generated by applying a strong radio frequencies electromagnetic field to a gas, which break down the gas molecules and generate the ions, free radicals, electrons, protons, photons, and reaction byproducts such as ozone. Since these reactive species have high energy, they create highly active and low temperature plasma, which can etch the material precisely and efficiently. This is the process for plasma etching. It's operate in both the high kinetic energy and chemical reaction between the neutrals and the substrate materials. The reactive gas that we are using, that is CCl2F2. In the carrier gas, ions produce reactive neutrals. These reactive neutrals attack in the both direction, means in the downward direction, on the side wall also, and the positive ions attack only the normal surface only. So etching is done more in this direction. The mechanism for dry etching is, first the feed gas introduced in the chamber, then it is break down into chemical reactive species to form the plasma with the high RF field. The reactive species diffuse on the surface to be etched and are then absorbed on the surface. On the reactive species, once this reactive species reach the surface, they move around the surface until they react with the exposed film. Afterward, the products of the reaction will dissolve from the surface. They are known as byproducts, and these byproducts are diffused away through the gas stream. In some process, the check temperature is increased to increase the speed of reaction. In case of plasma etching, though the depth is more than the side wall etching, but it's not etching properly, it means it's creating this angle, tapered trench it's creating, and these trenches are not desirable in some applications like canty pads, micro device with the overlapped fingers like. So RA process is introduced that will provide the MEMS structure with this aspect ratio, that is dimension of vertical to the horizontal. So the aspect ratio about 30 vertical walls, and this angle is about only plus minus 2 degree. So in recent new development technologies, we can get the aspect ratio about 100, means it's only etching in the vertical direction, not in the horizontal direction, and the depth is about 300 micrometers we can get. What is RAE, reactive ion etching? It uses the chemically reactive plasma generated under low pressure, that is 10 to 100 millitorr, to consume the materials deposited on the wafer along with the non-reactive ionic bombardment, which can make certain area of the wafer accessible for chemical reaction. In the RI system, the chuck holding wafer is grounded and another electrode is connected to the RF power source with the frequency that is 13.56 megahertz. Since electrons are more mobile compared to the positive ions due to their lighter weight, they travel along the distance and collide more frequently with the electrode and chamber wall and are consequently removed from the plasma. Means in plasma there is only the neutral ions and positive ions. This process leaves the plasma positively charged only. Nevertheless, plasma turns to remain neutral charge, thus the DC dielectric field is formed. And the region of the surface in the chamber and electrode is called darkneath. The reactive ion, beside the chemical reaction between the plasma and the target material, the positive ions can be accelerated. The negative ions are just absorbed, removed, and the positive ions they are accelerated towards the cathode due to this RF source electric power, and they will be absorbed by the surface. The process is the physical bombardment, which can also be assist the etching process. The RI has the probability to move the etchant in the direction of electric field and produce more anisotropic etching. Because of this electric field, these negative ions, these positive ions, they are moving downward, so they will etch it anisotropically. Next is inductively coupled plasma etching. In case of inductive coupled plasma etching, two separate power supply are used to independent control for the current and the ion energy. ICP, inductive coupled plasma source, generate a high density plasma due to the inductively coupling between the RF antenna and the plasma. The antenna located in the plasma generation region create an alternative RF magnetic field and induce the RF electric field, which energize electrons and particles in the ionization of the gas molecules and atoms at the low pressure. Due to the absence of the electric field near the reactive walls, there is virtually no ion bombardment or erosion of the walls. See in the diagram, as we are using, these are the inductive coils we are using, and separate power this for energizing the plasma, and one is the R field is we are providing here, electric field is providing here to provide the direction of this plasma. A separate power source is connected to the cathode in order to generate the DC bias, and it attract the ions to the wafer. That it become possible to decouple the ions current and ion energy applied to the wafer. Means there are different energies we are using, but for energizing this plasma, that is the inductive coupled energy we are using for that one. And second one, different separate DC biases we are providing that will attract these plasma towards the surface of the wafer. And because of this, more anisotropic etching is possible here. Sorry, more isotropic than array. These are the some YouTube links. You can go through this for more information. Now the difference between the wet etching and the dry etching, you can see the profile in the dry etching. That is a very good profile we are getting. It's only etching in this particular direction, but in vertical direction, but in case of wet etching, it's etching lateral direction also, so we are getting the curved surfaces in the substrate material. Extent we are using in the wet etching, there are the chemicals, and in case of dry etching we are using ionized gases. The directionality is only with the single crystal material we can get the aspect ratio up to 100, but in case of dry etching it's good for most material. Higher energy meaning more directionality we can get. Environmental impact are low in case of dry etching, but in the wet etching we are using the chemicals, so there is a high environmental impact on this one. The masking film adherence is not as critical in case of dry etching. Simple mask we can use, but in photoresist may be used as a masking for, but in case of wet etching, simple photoresist can't be used. Another layer for masking we have to use, as we have studied during the wet etching process. Selectivity in the wet etching is very good, more than 100x, and in case of dry etching it's poor. Material to be etched, only certain material we can etch in case of dry etching, and in case of wet etching almost all the materials we can etch. The critical dimension control is very good in case of dry etching. In particular direction etching we can done, but in case of wet etching it is very poor. Equipment cost, no doubt, in wet etching is very less expensive, and in dry etching we required a vacuum enclosure, so it's expensive. Etch rate in case of dry etching is slow, that is 0.1 micrometer per minute to about 6 micrometer per minute. In case of wet etching it's about 1 micrometer per minute and above we can get. And control on the etch rate is good in the dry etching, but it's difficult for the wet etching, and we use the etch stop process. The throughput in case of dry etching is low. A single wafer we have to treat at a time, and in case of wet etching a bulk batch process is possible, so high throughput is there. But we already discussed that wet etching is mostly done for the wafer preparation, during wafer preparation, and means for cleaning, for smoothing of the wafer, and dry etching for other process. These are the references. Thank you.